When we use a large excess of alcohol in the presence of a ketone or aldehyde trying to drive the equilibrium toward the hemiacetal side, if we use more than two equivalents, we open up the door to nucleophilic substitution of the hydroxyl group in the hemiacetal for an alkoxy group, which gives a product in which there are now two alkoxy groups linked to the former carbonyl carbon, and this is called an acetal. Acetal formation is fundamentally a substitution process, and it's fundamentally a nucleophilic substitution process. So the mechanism, as we'll see in this video, is actually very familiar to you. It just uses a little bit off-the-wall leaving group, and it's a little bit offbeat because of the intermediates involved, but it is fundamentally an S-in-1 process. It's facilitated by acid, which also makes it a little weird looking, but at the end of the day, it's nothing more and nothing less than an S-in-1 process. What has happened here is the substitution of one nucleophile, the alcohol, which gets incorporated here, for another, water. The OH group in the starting hemiacetal gets incorporated into a molecule of water in the products. Because this substitution process is reversible, the leaving group H2O is not particularly stable relative to the nucleophile ROH, we need to do something in a Le Chatelier's principle sense to drive the reaction toward products, and we can do that by removing water somehow from the reaction medium. The mechanism fundamentally is an acid-catalyzed substitution process. Now remember, keep in mind that acids activate electrophiles. The purpose in life of an acid catalyst is to activate the electrophilic portion of a reaction mixture. And in this reaction, the electrophile is the hemiacetal. The alcohol will be serving as a nucleophile. And so the first step of this mechanism is activation of the electrophile by protonation of a group that ultimately becomes a leaving group, something that departs with a pair of electrons, or a nucleofuge. And here, that's the hydroxyl oxygen. Now, of course, this isn't the only basic oxygen within the hemiacetal, but it's the only one that's going to drive the reaction forward. It's the only one whose protonation is going to lead to the loss of a leaving group that produces the acetal product. Protonation of the alkoxy oxygen would lead back to the starting carbonyl compound, and that occurs under conditions, for example, hydrolysis conditions, when we're trying to get this reaction to go backwards. Protonation of that hydroxyl oxygen has established a good nucleofuge, H2O+, in the protonated hemiacetal intermediate. And from here, I want to emphasize the mechanism is purely SN1. Recall what happens in an SN1 reaction. First, the leaving group departs with a pair of electrons. This gives rise to a carbocation intermediate. Now, in the context of a hemiacetal, we can also involve the adjacent alkoxy oxygen in electron flow and call this a beta elimination step. Strictly speaking, this isn't required to do, right, since the carbocation structure and this oxygen cation structure are just resonance forms. We don't have to draw this curved arrow, but I like to draw it because it justifies the departure of water. This alkoxy oxygen is in some sense helping the water depart with a pair of electrons. That's why I label this an E beta step, although you totally could draw this as simply dissociation of a nucleofuge in step 2. Now we have actually a carbonyl type carbon at the center of this intermediate in the presence of a good nucleophile, the alcohol oxygen. And so, as I've drawn it here, a nucleophilic addition step can take place. And this gives an intermediate structure in which we've really established both carbon-oxygen bonds that we need to form. We now have two alkoxy groups linked to the former carbonyl carbon, but one of them is protonated. We generated water way back in the first proton transfer step, and to regenerate the catalyst and generate the neutral product, we must transfer a proton back to that water. Before I draw that, it's worth mentioning that if we drew the alternative carbocation resonance form of this intermediate here, this would be an A sub n step, and that DNA in sequence is the hallmark of SN1, which is the reason I mention it as an alternative. Really, the only difference is which resonance structure we choose to draw there. Returning to the proton transfer, when we transfer that proton back to water, we've produced the neutral acetal product. Now two alkoxy groups are linked to the carbonyl carbon, and we've regenerated the catalyst, H3O+. And so notice that we lost water here as a nucleofuge in this beta elimination step. And so on the whole, the products are a molecule of water and the acetal. Like the hemiacetal, the oxidation state of the former carbonyl carbon in the acetal is +2. and it's characterized by two alkoxy groups linked to a common carbon atom. That's the hallmark of an acetal. So this substitution process, again, doesn't result in a change of the oxidation state of the carbonyl carbon. It's just a substitution process. The essential mechanism of its formation from a hemiacetal is SN1, and when we place a carbonyl carbon in the presence of excess alcohol in an acid catalyst, we should expect the reaction to go all the way to the acetal product. And so, just as a note here, except in exceptional circumstances that we'll talk about as specific cases later in the course, when you see an alcohol in the presence of a ketone or aldehyde, an acid catalyst, take it all the way to the acetal. Don't stop at the hemiacetal stage. Usually it's impossible to isolate the hemiacetal anyway when we use excess alcohol.